All right, today we're going to be talking about periodic organization and electron configuration. Everyone just did an alien card sort, and hopefully what you found out is that the rows are organized by body type with an increasing number of fingers going across, and the columns are by hair type, and it's increasing going down. And if you're wondering after doing that activity, what's the point of that? Well, the rows represent the number of energy levels, and the columns represent the number of valence electrons. So let's kind of dive into that a bit further. So what do we know so far? We know that when we have these electrons, we put them in these different rings. And we start with the innermost ring, and we put them depending on how many electrons we're talking about. So if we're talking about hydrogen, it only has this one valence electron. And then there's helium, and there's only two that go in the first ring. And that's because there's only two in the first row. Then, and this is a review, by the way, but for those who weren't here, I think on Tuesday, this is perfect for you. Then we put them in the second ring, and we have 1, 2, 3, 4, 5, 6, 7, 8. We put 8 valence electrons in the second ring. We're done with the row, thus we're done with the ring. So for every single row, we add a new ring. So now with sodium, I'm on row 3. That means I'm on ring 3. So I have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And then bam, I'm done with row 3. I'm on to row 4, aka ring 4. And I got potassium and calcium, and that's kind of where we ended. Okay, so this right here is element 20. We're at calcium. Okay, and this is the Bohr model for calcium. Now check this out. Another concept that we have is the concept of a valence electron. The valence electrons are the electrons in the outermost ring. So for calcium right here, we have 2 valence electrons because we have 2 in the outermost ring. Okay? Okay. Remember, when we go to a new row, we have new rings. So that means if I'm looking at my periodic table, and if I ask you how many rings something has, you just need to count what row it's on. So if I say, how many rings does argon have? You go, oh, it has 1, 2, 3 rings. How many rings does potassium have? You go 1, 2, 3, 4, 4 rings. Okay, so the rings, the number of energy levels is represented by the rows. Okay, that's how this Bohr model works. Awesome. Now let's talk about valence electrons. Now when we were doing this, skipping the very first one, we had 1, 2, 3, 4, 5, 6, 7, 8, and then we started all over. 1, 2, 3, 4, 5, 6, 7, 8, and then 1, 2, 3, 4, 5, 6, 7, 8, right? Well, perfect. So on your paper copy of this right here, you'll notice on the top it says valence electrons. So you can actually, and there's a little spot for you to write this in. You can say, okay, 1, for every single element in this column has 1 valence electron. 2, these ones have 2. And then we're going to skip all of these in the middle right here. We're going to go to the one that's above boron. And we go 3, 4, 5, 6, 7, 8. Those spaces on your periodic table is a spot for you to write those in and represents how many valence electrons are in that column. It's great for your homework. It's great for the quizzes. Yes, you can use it on the test. All right, cool, cool. This right here is not on a notebook page right here. This right here is a paper that you should have received from Beaverton School District at the beginning of Q3. It's an actual paper, okay? It's an actual paper. Now, you can go to ptable.com. It won't have this little bit at top. If you do not get that, you can go to the school and ask for it, okay? I designed it for you, okay? Okay, so what you'll get here is this concept that kind of looks like this, that everything in this first row has 1 valence electron. Everything in this second row, column, sorry. First column has 1, 2, 3, 4, 5, 6, 7, 8. And we're skipping all of these and we're skipping all of these. And this one right here has 2. Why does this one has 2? Well, it's in the first row and the first row only has 2 to be full. Okay? Okay. So what about these other spaces? Well, it's a little bit more complicated than that. I'm going to try and simplify it, but it's actually kind of crazy. These things have letters associated. This is an S block, a P block, an F block, and these are D blocks and everything like that. And technically, these are 3-dimensional shapes. And technically, when you're going across, we can stuff electrons underneath the outermost shell and double stuff. But you know what? We're not going to get into it really, okay? Not too much right now. But this right here is called the D block, and this right here is called the F block. And we're going to talk about those for a moment. Okay, so check this out. The number of valence electrons, we're going to oversimplify it for right now, is 2. Everything in the middle has 2 valence electrons. Everything down here has 2 valence electrons. So if you want to add that to your physical copy of your valence electrons, you can say, bam, this right here has 2 valence electrons. All of these and all of these. Okay, so next thing that you need to notice, all right, is let's look at these different numbers. All right, they obviously increase 52, 53, 54, 55, 56, and then look at this. It says 72. Where's number 57? Number 57 is down here. Technically speaking, this whole F block gets put into right here. And look where it ends up. It ends at 71, and then the next one is 72. So the real periodic table is actually like this. That's the real periodic table. Well, if you're asking yourself, well, why don't we look at it like that? For 2 reasons. One is for graphic design elements, right? It just makes it super long and skinny, and that's just really tough if you're on graphic designing, okay? So what they do, and also we just don't use these ones down here that often. So what we do is we make a break and we put it in there. So in my beautiful periodic table, you can kind of see this break, all right? That 57 and 70 through 71 kind of go right in there, okay? So if I ask you, well, how many rings does, I don't know, uranium have? Well, now you know that uranium has, that uranium right here fits into this row right here, okay? See, 88, 89. So it fits in right here. So technically it has 1, 2, 3, 4, 5, 6, 7 rings. Do you see what I'm saying? The main things, though, that you need to know are kind of in this graph, in this slide right here, okay? That everything right here has 1 valence electron, 2. All of these will have 2. All of these have 2. In reality, it's not really like that, but it's an oversimplification, and we're cool with that. We understand that models have limitations, and that's where we are in our understanding right now. 3, 4, 5, 6, 7, 8. Okay? Okay. So we can put some notes in right here. Takeaways from the notes. What's going on in the rows? Rows represent the number of rings, aka energy levels, okay? Columns represent the number of valence electrons. Number of valence electrons, same throughout a column, and it's 2 in the center. All right, next thing I'm gonna have you do is watch this little video and answer these 2 little questions about our dude Mendeleev and his organization of the periodic table. So the last thing that you need to do is you basically need to be able to identify some different stuff about these elements. So let's say it takes sulfur, S. It's right here, okay? So I know just by looking at it that its atomic number is 16. And for the sake of this activity, I'm going to say that the number of electrons is always equal to the atomic number, that it's not an ion. So these 2 numbers are always going to be equal for this activity, okay? So if there are 16 protons, there's going to be 16 electrons. Now, the next thing is I need to figure out what ring it's on. So here's sulfur. And remember, it doesn't start right here. It's up here. It's 1, 2, 3. It's 3. Bam, it has 3 rings. And the number of valence electrons, well, if you wrote them in there, you can just look up above, or you can just count going backwards. I go 8, 7, 6. So this would have 6 valence electrons. Okay? Okay. I want you all to work on these ones right here, doing that same process.